We know how to compute sums of matrices and integer powers of a matrix A, but can we do more? Can we compute other functions like e to the power A or sine A and others? Yes, we can. We can use power series. In this video, you will learn how we can use such a power series to compute e to the power A. So we know that if we have some x in R, a real number, how to compute e to the power x. E to the power x can be written as a power series, sum from n to infinity x to the power n over n factorial. So that equals 1 plus x squared over 2 plus x cubed over 6 and so on. That is for e to the power x. Now we can extend this idea to e to the power a, where a is a matrix. For e to the power a we define similarly sum n from 0 to infinity and then a to the power n divided by n factorial. So that is identity matrix plus a squared over 2 plus a cubed over 6 and so on. So in order to compute e to the power a, we need to be able to compute a squared and a cubed. We know how to do that, and we have to be able to add matrices, and we are also able to do that. So how does this work in an example? So we need to compute a to the power n, so that works particularly well if A is a diagonal matrix. And that will be our first example, first case. A equals D diagonal. And then compute e to the power D. So let us take a 2 by 2 matrix. For larger matrices we will do exactly the same. So it suffices to take a look at a 2 by 2 example. So diagonal matrix, so put lambda 1 and lambda 2 on the diagonal. And then we know how to compute d to the power n. That is just lambda 1 to the power n and lambda 2 to the power n on the diagonal. Now we can plug this into the formula for e to the power a over here. So what do we get? E to the power d is sum n from 0 to infinity, 1 over n factorial, and then d to the power n. That is the definition. And we know what we have for d to the power n. It is just lambda 1 to the power n and lambda 2 to the power n on the diagonal. Then we can put in the n factorial, of course, so we get the lambda 1 to the power n over n factorial, similarly for the other component. And then we can add all the matrices, which is just adding all the lambda 1 to the power 1, etc. So we can take the summation in. And then we recognize something. The summation n from 0 to infinity lambda 1 to the power n over n factorial, that is just the power series of e to the power lambda 1. And the other power series over here is just the series of e to the power lambda 2. So what do we get if we compute e to the power d? Well, that's actually pretty easy, as you see in the result. If d is lambda 1 lambda 2, then e to the power d is just e to the power lambda 1 e to the power lambda 2. And that is of course because d is such a nice matrix. So what happens if you make life slightly harder? If you say a is not equal to d, but a is similar to d. So a equals p times d times p inverse. What then? Well, again we will need a to the power n. So let's see what happens if you compute a to the power n. So a to the power n equals a times a times a times a times a. So n times is p dp inverse. And then you see those p inverses and p's in the middle all cancel out. So what we are left with is the first p and the last p inverse, and d times d times d times d in the middle, so d to the power n in the middle. So what do we get for our e to the power a then? Well, again, sum n from 0 to infinity and the 1 over n factorial. And here we have our a to the power n. And now we can use the following trick. Both the p and the p inverse do not depend on n. So they are basically constants with respect to the summation, so we can take them out of the summation symbol. On the correct side, of course, because we are still working with matrices. So the p goes in front and the p inverse goes in the back. And what you're left with is a p inverse here, and a summation which now only has the d to the power n. But we recognize this. The summation in the middle is nothing else than our e to the power d. So what we have if we compute e to the power a is p times e to the power d, which we already could do, times p inverse. So let us look at an example. If we have our d like this, then we can immediately compute e to the power d. It was just e to the power 4 and e to the power minus 1 on the diagonal, so that's easy. And second example, if we have our A like this, not a diagonal matrix, but now A is similar to a diagonal matrix, with this P over here, and with the D over here from example 1. You can check that, just compute eigenvalues and so on in the normal way. Then we know how to compute e to the power A. E to the power A equals P times e to the power D, which we already had from example 1, times P inverse, which is the matrix P, compute the determinant, which is 5, so you have a 1 over 5. Switch the numbers on the diagonal and minuses on the off-diagonal terms. So there we are. There we have our e to the power A. And of course you can compute it by computing this product of three matrices, but it's, I think, a bit more insightful to leave it like this. One note, one warning though, you have to be a bit careful with the familiar rules, because e to the power x plus I equals e to the power x times e to the power y. Now for matrices this only works if AB equals BA, because when computing like all those powers you have a plus b squared and so on, and then you have a squared plus b squared plus ab plus ba, and you want to be able to turn it into 2ab. So in order to be able to do that, you need to be able to switch the order. So this only works for commuting matrices. So that is how you can compute the matrix exponential. Works nice if A is either D or similar to D, and you always have to be a bit careful here, for example with the commutation.